Hi AP Stats, this is Mrs. Cowles, and today we're going to take a look at Chapter 2, Notes and Examples for 2.1 Part B. So again, the goal of this video is for you, if you're watching it for the first time, is to just watch and listen, pause, then go back and fill out. There will be a scanned key of the notes online as well. As you come up to a check understanding, you should pause the video and see how you do and then turn it back on and check it out. Okay, so let's get started. For the first learning target today, we're going to describe the effect of adding, subtracting, multiplying by, or dividing by a constant on the shape, center, and variability of a distribution of data. So let's take a look at the example below. Here we have a graph and table of summary statistics for a sample of 30 test scores. The maximum possible score in the test was 50 points. Suppose the teacher was nice and added 5 points to each test score. How would this change the shape, center, and spread of the distribution? So let's take a look here. We have our original test scores for our 30 students plotted, and then we have their test scores plotted when we add 5. So as we take a look at the distribution of our data, we see that even though we added 5 points to every test score, the shape stays the same. So adding 5 points to each observation, the shape does not change, it stays the same. How about the center? Well, when we take a look at the mean and we take a look at the median, we can see that they both increased by 5. So adding 5 points to the original data value will increase the measures of center, the mean and median, by 5. When taking a look at variability, we can talk about standard deviation, IQR, and range. And as we take a look at our measures of spread or variability, we see that none of them changed when we added the 5 points to the test scores. So variability will stay the same. So from this, we want to see the effects of adding or subtracting a constant to each data value will add, let me repeat that. Adding or subtracting a constant to each data value. So if we add A, the same number, A, to each observation, it's going to add A to our measures of center and our measures of location. Again, location is our minimum, our maximum, our percentiles, Q1, Q3. All of those values, along with our centers, will have that constant A added to them as well. We saw, though, that when we add or subtract a constant number A to our original data values, it does not change the shape of the distribution or the measures of spread. This is something that you need to know and understand. So definitely make sure you summarize this at the end of your notes. So taking a look at this question, it says if 24 is added to every observation in a data set, the only one of the following that is not changed means what stays the same. Well, if we take a look at A, the mean, we're going to add 24 to the mean, so it will not stay the same. Adding 24 to every data observation will add 24 to each of our location values. So our 75th percentile is our Q3, so that will have 24 added to it. It will change. The median is a measure of center. Adding 24 to each observation will add 24 to the median. But the standard deviation is a measure of spread or a measure of variability. We saw that adding a constant to each original data value does not affect the spread. So therefore the answer is D. And again, you can see a proof down here below that explains why the IQR will stay the same when adding A. Okay, so let's take a look at the next example. It says, suppose the teacher in the previous example wanted to convert the original test scores to percents. Since the test was out of 50 points, he should multiply each score by 2 to make them out of 100. Here are the graphs and summary statistics for the original scores and the doubled scores. What happens to the center, the location, and the spread? So as we take a look at this, we can see that as we look at our data and we have doubled our scores, that the shape stays the same. The shape did not change. But let's talk about our measures of center, our location, and spread. When we measured our center, we see that the mean and median, both of them doubled from our original to when we multiplied by 2. We take a look at our measures of location, we can see that they also doubled as well. And same thing with our measures of spread, our standard deviation, our IQR and range, they also doubled. So multiplying each of the original data values by 2 will double the center, location, and spread. And we already observed that the shape does not change. So the effects of multiplying or dividing by a constant If we multiply or divide each observation by the same number b, we will multiply or divide our measures of center and location by b. We would also multiply or divide our measures of spread by the absolute value of b, but we see that multiplying by a constant b will not change the shape of the distribution. Again, this is something you need to know and understand, and it'd be a good idea to summarize that at the end of your notes. So, how do these transformations affect z-scores? So let's take a look. Suppose we want to standardize the original test scores. This would mean we would subtract the mean of 35.8 from each score and then divide by the standard deviation of 8.17. So standardizing means converting to z-scores, so that's what we want to do. How is this going to affect the data of our z-scores? How are these transformations going to affect it? So let's think about this. When we're converting to z-score, we are going to be subtracting and dividing. How will that affect the distribution of the shape of the z-scores when we would plot it? Well, we saw earlier that subtracting and dividing does not affect shape at all, so the shape will stay the same. Let's talk about the center. And specifically, we're going to talk about the mean. So, when we take each of our data values and we're going to convert it to the z-score, the first step is to subtract by 35.8. So, if we take a look, when we are subtracting by the constant of 35.8, that means we're going to take that constant and subtract it from our mean. If we look at our original mean, it's 35.8, so when I go ahead and subtract 35.8 from 35.8, that's going to leave me with 0. So subtracting 35.8 would reduce the mean by 35.8, making it equal to 0. Now, what happens next is when we're converting to z-score, after we subtract by 35.8, then we're going to divide by 8.17. So we would go ahead and we would take that mean, x of 0, and we would divide it by 8.17. So basically, I would have x bar, which we had equal to 0, and we would divide that by 8.17. And when we do that, we are still going to have a mean of 0. So when we are standardizing scores or data values, when we're converting them to their z-scores, we're going to find that no matter what set of data we use, when we convert it to the z-scores, that the mean of the z-scores is always going to be equal to 0. So how will these transformations affect the spread? So let's think about this. Once again, our original spread, and we're going to talk about our standard deviation for this spread. So our original standard deviation for our test scores was 8.17. So when we're going to convert to z-scores, the first step is to subtract 35.8. As we saw earlier, subtracting does not affect the spread. So in our first step, subtracting 35.8 will not change the standard deviation. So we're still going to start out with the standard deviation of 8.17. So subtracting 35.8 would not change the spread. Now, the next step, after we subtracted 35.8 to find the z-score, we're going to divide 8.17. Now, dividing does affect the spread. So in this case, we started with a standard deviation 8.17. When we subtracted the 35.8, it stayed the same. It did not change. But now we're going to go ahead and we are going to divide by 8.17. We know it's also going to divide our common measures of spread by 8.17. So the standard deviation would then be the 8.17 that we got from when the subtracting 35.8 didn't affect it. We would divide that by 8.17 and we end up with 1. The standard deviation of x will be equal to 1. So when converting to z-scores or standardizing, the standard deviation will always be 1. So this is something you're definitely going to want to summarize and put in your notes. At the end in your summaries is when standardizing, the mean of your z-scores will always be 0 and the standard deviation will always be equal to 1. So again, pause the video and try the check understanding and then check back in to see how you did. So in this example, we have a dot plot that shows the height distribution of Mrs. Navard's class along with a summary of statistics from the computer output. Suppose you have to convert the class heights from inches to centimeters. Describe the effect this will have on the shape, center, and spread. Well, in order to convert from inches to centimeters, you're going to have to multiply each of the heights by 2.54. When we multiply by 2.54, the shape is not going to change, but the center and spread will both be multiplied by 2.54. In the second question, it's Mrs. Navard had the entire class stand on a 6-inch high platform and then had the students measure the distance from the top of their heads to the ground. How would the shape, center, and spread of distribution compare with the original height distribution? Well, each height would have 6 inches added to it. When we add a constant, the shape and spread will not change, but the center will be affected, so the center will have 6 inches added to it. Now suppose that you convert the class's height to z-scores. You're going to standardize the scores. What would the shape be, the mean for your center, and the spread of this distribution? And when we're talking about spread, we're going to take a look at the standard deviation. So again, when converting to z-score, we're going to subtract the mean and divide by standard deviation. We know that subtracting and dividing will not affect the shape. So the shape of our z-scores will not change from the original shape of the heights distributions. Now, how about the mean? Now, again, the mean, if we take a look back at the top, it tells us that the mean is 67. Standard deviation is 4.29. So how is the mean going to be affected? Well, we take a look, we're going to subtract the mean 67 from each data value. So that means our mean of 67 is going to be brought down by 67 down to 0. Now I have to divide by the standard deviation, so that'd be 0 over the 4.29, so the mean of our z-scores will change to become 0. The standard deviation, when we subtract the mean from every data value, our standard deviation is going to remain the same. So under the first operation of subtracting, the standard deviation will still be 4.29. But then the next operation was to divide every term by the standard deviation. So we're going to take our standard deviation that we had and we're going to divide it by our standard deviation again, 4.29, which is going to leave us with 1. So the z-score, or the standard deviation of the z-scores, is always equal to 1. Again, you need to know that, but you also need to be able to show the mathematics to back your reasoning up as to why it is 0 and 1. Be ready to use the mathematics to explain. Okay, our next learning target is about density curves. So page 99 in your textbook will help explain this. If we take a look at the exploring quantitative data, we already did steps 1, 2, and 3 in chapter 1. When we look at quantitative data, we always want to plot it. We want to look for the overall pattern or shape, our SOCIV, our shape, center, outliers, and variability. And then we like to calculate a numerical summary to help describe the center and spread. Now, the new step that we're going to learn is sometimes the overall pattern of a large number of observations is so regular that we can describe it with a smooth curve. The smooth curve is called a density curve. You need to know the properties of a density curve. The density curve is always going to be positive. It's going to be above the horizontal axis, and we know that the area underneath it is going to be exactly 1. Now, this can be an example of a density curve. It doesn't always actually have to be curved. So we know that it's going to be positive. We also know that the area would be equal to 1. A density curve describes the overall pattern of a distribution. The area under the curve and above any interval values of the horizontal axis is the proportion of all observations that fall in that interval. So obviously from 0 to k here, we see the proportion would be 100% because it's the full area of 1. No set of real data is exactly described by a density curve. The curve is an approximation that is easy to use and accurate enough for practical use. Because a density curve represents a population of individuals, the mean is going to be denoted by mu, and the standard deviation is going to be noted by the Greek letter sigma. When looking at the median and the mean on a density curve, the median of a density curve will cut the area in half. The mean of the density curve is the balance point, and it would be the point at which the curve would balance if it was made of a solid material. The median and the mean are the same for a perfectly symmetric density curve. They both lie at the center of the curve. The mean of a skewed curve is pulled away from the median in the direction of the long tail. So go ahead and pause this and try the next check understanding. So the first question says, explain why this is a legitimate density curve. Well, if we take a look, everything is positive. It's above the horizontal axis, and it tells us here that the area under the curve is 1. So this is legit because the curve is positive everywhere, and it has a total area of 1. What proportion of observations lie between 7 and 8? We can see it's 0.12, so about 12% will lie between 7 and 8. Now, I want you to, on your graph, mark where the median is. The median divides the area under the curve in half. So we see it's not perfectly symmetric, so we know the median is actually going to be a little bit to the left of our center here, or of that peak, because of the long tail over here on the left. So to cut this in half, we are looking to draw that median so that we have half of the area to the left and half of the area to the right. Now, where would the mean be? Again, it's not perfectly symmetric. It has a longer tail on the left, so that tail is going to be pulling the mean in that direction. So we are expecting the mean to be to the left of the median. The mean is less than the median in this case because the distribution is skewed to the left. All right, so now it is up to you to go through and to summarize the big ideas from this lesson. Learning target number 1 and learning target number 2. Again, when you are summarizing, I definitely would suggest that you go through and make sure you make it nice and clear to yourself that what happens when you add or subtract a number to each value, and what happens when you multiply or divide by the number b to each value, how that affects your shape, center, and spread. Okay. All right. Thank you, AP Stats, and have a good night.